Hello and a very warm welcome to our second day of our little series of online seminars around the topic of testing data networks. My name is Alfred Huber I'm the technical manager here at Softing IT Networks, and I will take you to today's presentation. And I'm, as you can see, not alone today in the studio. So I got my co-pilot here who wants to introduce himself and his role of the day to you. So please.
Yes, hello, I'm Frank. Today I'm helping Alfred at the PC. In general, over here, I'm a technical sales. And at this webinar, you should see at the side one control panel. And at this control panel, there is an option questions, where you have a chat. You can enter your questions over there in the chat. I will collect them or answer them directly. Mostly collecting them and answer it after the session. And there is one option called handout, where you can download the PDF while the webinar is running.
Yes. Thank you very much, Frank. I think he explained his role very nicely. So please feel free to answer questions always during the presentation, not shifted to the end of the presentation. They might get lost. So this is Frank's job to answer immediately. And if it's interesting enough, we'll talk on the panel later on this. Okay, so what's the topic of the day? The topic of the day is fiber optic, basics of fiber optics. Yesterday, we started the series with the basics, very basics of copper networks. Today, we want to go to fiber optics, very basics. So agenda of this next hour is the introduction to the basics of fiber optics. First of all, of course, for the attendees which are new to us, a little introduction. Who is Softing? Who is Softing IT Networks? Then we talk about the basics of data transmission over light. We will talk about the components which are involved, the fiber optics, the cabling, the fiber itself, the connectors, and so on. Then we'll dig a little bit deeper and see what are the sources of losses of signal and faults in a fiber optic link. So that's only very on the surface. Then, of course, we're talking about fiber optic measurements, which we're standing for, our instruments are standing for. And an issue which is very important when you're dealing with fiber optics is cleaning, inspecting, dealing with contamination on fiber optic links. Usually we do it before, but today we decided to shift it to the end of the presentation because of its importance. As I said, this is a introduction to the topic of fiber optics. Next week, similar to the copper side, we will do also an advanced training course on this, an advanced seminar where we dig deeper into the technologies of testing the fiber optic links, so on. Today, it's just roughly on the surface to discuss how does it work to transmit data over fiber optics. So let's start first with the introduction of Softing. Who is Softing? I do it very quickly. Softing is a typically mid-sized German company founded in 1979 with about 400 employees, annual turnaround 85 million euros, founded, went public, the company in 2000. And we have locations worldwide spread. You see later on a map a little bit where we are located. Softing itself is a publicly traded company, and it's a holding organization which belong to certain companies belonging to this holding. The major three columns where Softing sits on is automotive, is IT networks, and is industrial automation. What are these three columns doing? The colleagues of the automotive group are specialized on producing test systems for ECUs, engine control units for cars. So they are very deeply involved into car and testing into cars or automotive in general. The other side, the industrial automation, what are these colleagues doing? These colleagues are helping people to set up production lines, let's say it's this way. A typical problem in setting up a production line is that every machine which is part of a production line speaks its own language, own field bus protocol. And it's very difficult sometimes to combine various machines talking various protocols into one production line. And there are certain instruments needed to connect the different stations, the so-called gateways. And Softing is one of the specialists in producing gate waves. Also in industrial automation, new tendency is to collect data next to a machine and to analyze the data where the machine got some trouble. That's on the side of the industrial automation group. We from IT Networks, we are sitting a little bit in between of the columns because basically we are coming from the area of structured cabling in offices and buildings. Why are we sitting now between automotive and industrial? Because we expanded the business. So our test equipment is not only testing structured cabling in buildings, but we also are testing now structured cabling, kind of structured cabling in industrial environments and even in the automotive stuff. Because what's in automotive? It's the same tendency we had in the office environment years ago, that Ethernet is going to move into that area and is definitely overruling all the other applications and protocols. So the same is happening industrial environment. The field buses, all this variety of field bus protocols is now slowly exchanged against Ethernet. So there is a combination of IT and OT, as we can read everywhere, and everywhere where Ethernet moves in, if it moves in a car or in an automated situation, when Ethernet moves in, it needs testing of the physical structure where it's transmitted. So Ethernet depends and relies on a working infrastructure, on a working hardware or working cables and links to run properly on this. And the testing of those Ethernet links, that's what we are known for. And since we do it for many years now, it's interesting for us to expand a little bit our business now into the areas of automotive and also industrial environment. That's all for the quick introduction of Softing. So we have a lot to talk about, so let's hurry up a little bit on the general introduction. What you see here is a sorting order where we sort of how we sort our test instruments, or the most important test instruments we offer. So the very low level we start here is the extremely low level, the Wi-Fi network device. We call it a Wi-Fi sniffer. Actually, I call it an intelligent antenna. So this antenna is capable of collecting data over the air in enormous amount and provide this data collected to an intelligent analyzing tool like Wireshark, for example. So the guys who are involved in analyzing protocols and so on. It's a little special instrument. Most of the instruments starting at the verifier level. Verifier is just a very basic instrument. For example, testing only wire map on a copper cable. So that's the level of wire verifiers or verifier instruments. The next level above the next level above the verifiers is the qualifiers. Qualifiers are also testing links, copper and cable links, and they already examined the performance level of a transmission link, and qualifiers are doing this through testing through the actual protocol. So a qualifier is typically using the Ethernet protocol, sending data over data link, and is looking for losses in the data communication. And if you don't lose over a certain time any bit in the transmission path, you can tell the customer, hey, this link is also capable to run 1 gigabit Ethernet, 10 gigabit Ethernet, whatever. Okay, the top level of these products, of the instruments, is the certifying level. Certifying typically acceptance testing of a transmission link, either on the copper side or on the fiber optic side. So it's I call it the master class for doing the measurements. It's really measuring devices, not just testing devices. And more about the certification you'll see also next week in the advanced course. Okay, that's about the products. Where are we on the world? So here you see the locations where you find major branches from Softing. So Munich, as you can see in the middle, is the headquarters of Softing, and also product market management, and these things are done from here. We have a very large brand in Knoxville to handle the Americas. We also have a very strong R&D department and sales department in Singapore, handling the Pacific Asia area. And we have a dedicated sales office for China, which sits in Shanghai. In Europe, we have individual offices like Paris, Barcelona, Milan, and Vienna. So from there, the European business is controlled. Okay, let's dig into the topic. data rate trends. I think everybody has seen this picture before. It's about the evolution of network speed, of Ethernet speed. And I don't want to go into details on this, but everybody is aware it's getting always faster and faster and faster. I remember the days when we started off with 100 megabit Ethernet, and then we crossed in the 90s the 1 gigabit Ethernet on the office environment. Nowadays, we are building networks which are minimum capable of running 10 gigabit Ethernet in the network. In the data center, networks should provide capabilities up to 40 gigabit on copper. And if you look into fiber, we're talking about 400 gigabit Ethernet. So there's only one direction, and it goes straight up. The higher the speeds are, the more you need testing, and the more precise testing has to be. But that's topic of later. Okay, so let's look back to the classical environment, the office environment. So here is again our challenge. We have a company which is located in 3 buildings on a certain area, on a certain campus, a local area. And the first job we have to do is now to connect these 3 buildings together to allow communication between the buildings. How is this done? It's done on the primary level, as it's called, and this is done through fiber optic, the topic of the day. Usually we use here single mode fibers. Single mode fibers are the choice for long distance, high data rates, typically the long distance, the connection between the buildings. In the building, we also use fiber for the secondary level, the backbone, the classical one. This is typically multi-mode. Okay, we will see later on what is multi-mode, what is single mode, quick definition of this. When we come to the floor level, to the 3rd level, it's changing the media. Most of the time, you're changing now from fiber optics to copper. Why? There is tendency since years going on that copper is important because of an application called PoE, power over Ethernet. So everybody tries now to feed the end termination instrument with the power from the switch, for example. So we don't want to have a separate power line in a separate data line. So the combination of data transmission and power transmission, PoE, requires copper. And copper gets more stronger as ever before. I remember about 20 years ago, the fiber optic people always told us, hey, this copper stuff will be dead in 10 years. No, it's turning the way around. So on the floor level, copper is as strong as ever before because it can transmit power. And it's actually still cheaper to use a copper system, combined switch and cabling stuff, as to use a pure fiber system. Okay, so that's the 3rd level we don't talk about today. We did yesterday already. And the 4th level is the Wi-Fi level. No network nowadays without Wi-Fi, but not topic of this series of seminars today. So now let's look to the fiber optic side. So here are 2 different ways to build a fiber optic network up to the level, let's say, to the level of the floors. There is basically 2 systems. One is the distributed backbone, as we call it. So distributed backbone is the one we typically build nowadays. So you have a one distributor in the building, and this distributor from the building is going to distributors on the floor, as you can see here. So a central distributor, and is going to individual floors. Okay, so this can be done by fiber optic and also sometimes copper if you have no potential difference between the floors. And typically here we're switching to copper, but we also can of course go to fiber to the desk. No problem on this. Fiber connection between the buildings, very important here, fiber optic for the high data rates, for the long distances, to avoid any potential problems. Okay, but you can also have a different system and you purely do a fiber network, fiber optic network. This is called the collapsed backbone. So what we are doing here is we don't use the floor distributors. We just have one building distributor and we just take a fiber optic line down to the individual outlet in the different areas. So possibly to do, these are the 2 ways you definitely can construct a fiber optic network. Okay, that's about the way how to construct it. Let's see how it works that we can get data transmitted with light. So here's an interesting table a colleague compiled together. One very important feature to select the proper media to transport light is the optical attenuation. Optical attenuation means I have my transmission media here and I put some amount of light here in, and I expect to get some amount of light out of here. And the loss in between, the attenuation, is a very important factor. So if you would take, for example, to transmit light, Rhine water from the River Rhine, it would have an attenuation of about 100,000 dBs per kilometer. And 50% drop in light would happen after 0.033 meters. So I think Rhine water is not very good for transmitting light signals over a certain distance. Let's look for something better. Let's go for window glass. Typical window glass, we don't have your windows. So if you look to the window, you have an attenuation of about 50,000 dBs per kilometer. So half of the light gets lost after 0.066 meters already. Also not the best media to use. Oops. Something went wrong here. Give me a second to adjust it again back. So optical glass, typical glass is used for glasses, has an attenuation of 3000 dB and so on, and you can go through the list: dense fog, city air. Who wants to transmit signals via city air? Good fiber, that was in the beginning of this fiber optic stuff in the 1970s, had about 20 dBs per kilometer, and it was fantastic clean fiber, and everybody loved it. And we could really transmit data over fiber. Nowadays, we are down to about 3 dBs of attenuation for a multi-mode fiber, about the kilometer. Single mode fiber, the newest, the latest one, OS2 quality, we're about 0.4 of a dB per kilometer. So you can really use it for long distance. So you can build up networks about 40 or 100 kilometers without any amplifier in between. Fantastic for long distance data transmission. Last row is plastic fiber, officially called polymeric optical fiber. That's used for short distances, for example, in machineries. The industrial environment is very often using these plastic fibers. They have very high attenuation as well, not typically built for data transmission over long distance, but it should be mentioned because it plays some role, especially in the automotive range. What is light? We all learned in school, light is a mixture of a wave and parts. So, and we have an electromagnetic spectrum where light is part of this. And a colleague did a very nice job here in compiling a lot of application on the electromagnetic spectrum. So if you start very low with very low frequency, very long waves, we're about AC main supply, AC power, 50 hertz, 60 hertz, everybody's aware about this. If we move up the ladder here, these orange buttons, we are in the radio, in the television radio broadcast area with the frequencies 100 kilohertz up to 100 megahertz, something like that. If we move higher in frequency and going up to the next range, it's about the microwave range. Microwave, everybody's aware, 2.6 gigahertz, 2.4 gigahertz, same frequency as mobile phones, for example, use. There is no light up to now, so we have to increase now these frequencies or shorten the wavelengths. So the next area, now we're coming close where we want to go. Now we are in the range of the microwave still in the 100 gigahertz and terahertz even. Then we got the yellow line. The yellow line gets interesting. And after this yellow line, we are in the wavelengths or the frequencies about X-ray radiation. So everybody who went to doctor already, had some broken leg or something like this, got some experience with X-rays, not to help see very much. So you have to be very careful when using X-rays and properly using. And above that wavelengths, you are on the gamma radiation. So it's really dangerous, and you see what's happening if you too long on gamma radiation. So where is the light now? The light now sits now in the yellow bar. So here is a spectrum of the visible light. So open it up, spread a little bit, and now you can see that the visible light is in a frequency, in a wavelength range between 780s down to some 400 nanometers wavelength. This is visible light. Do we use the visible light in data transmission? No, we don't. We are using infrared light, which is above this level or below this level. So This friend can't see these lights. No one can see the light, so it's infrared definitely. And we picked three optical windows out of this electromagnetic spectrum which we use for data transmission. The one is around the 800 nanometers, the other one is around the 1200, 1300 nanometers, and the third one is around 1500 nanometers. These were the basic start of the windows used for data transmission. Nowadays, the windows are opened up to the higher wavelengths. So the fourth window has opened up, and some windows in between are used now for dense wave multiplexing, all these fancy things. Let's reduce it back to these three windows we know. Why have we chosen these three windows? Because these three windows are very nicely fitting into the attenuation performance of glass. And here is a chart which shows us the loss characteristics of optical fiber. Here you see the wavelengths, and here you see the attenuation amount of light you lose. Okay, so what you see here is the characteristics for a typical glass for fiber optic. Okay, and you see we have not a linear line. We have peaks in our curve. We have here a very high peak. These peaks are stemming from hydroxyl ions which are sitting in the material. They are called water peaks. Okay, and these water peaks are increasing on these 3 points, increasing the attenuation of the fiber optic. This is the reason why we have chosen windows which are outside of these water peaks. So the first window is around the 850 nanometers. Then we have the 1300 nanometer, which just falls in between this water peak and that water peak, and the higher ones up to 1500, 1600. Okay, as I told earlier, this high water peak is not very nice, because a lot of people in the single mode area started to use that wavelength as well, wanted to use that wavelength as well. And nowadays, a very modern single mode fiber optic cable has this shape. You see, the water peaks are more or less eliminated, except the big one, but this can be tolerated and can be used. And so we can also use multiplexing in herein. We also use certain cases multiplexing on multi-mode, but this is always in this range where the water peaks is definitely out of the range. Okay, that's about the loss characteristic of optical fiber. So let's have a look to the fiber itself. Colleague got some nice slides, older slides to be honest, about the different setup of construction of data cable, and you see the fiber optic is always within some other surrounding tubes, and you got different material out there, some metal sometimes. So this is typical kind of cable that are used in the outside, typical cable used in the inside. These kind of cables are typically used connected by splicing. So that's just a method of melting together fiber optics. In the in-house area, to come to the end units, you got also breakout cable cords. These cables are terminated with fiber optic connectors. There are different setups and construction of how this fiber cable is surrounded by other cables and how many are in one actual cable sheet. So there are different constructions, and these cables are then filled sometimes with gel, and there is loose tube dry, not existing anymore in older days, where the fiber optic cable was just freely moving in here in these 900 micrometer or 2 millimeter micron surrounding and so on. So these are different types of how the data cable can be constructed. Not of our interest, honestly, for data transmission. This is more mechanical stuff. So we want to go on and to see where it's getting interesting for us. And if it gets interesting for us, we look to the inner part of the fiber optic cabling. So the part which is interesting for us is the first one on the outside is the primary coating, the primary polymer coat which is holding the actual fiber that is transmitting the data. This material is used to make it flexible because, as said, it's fiber optic, it's glass inside. Glass typically is not very flexible. To get glass flexible, you need to coat it by some plastic, let's say. And this is the primary coating which sits around the fiber optic, the glass, and the diameter is around 200 more to 250 micrometers. Inside this primary coating now, we see the two different materials, or we get the two different materials of glass. So the outer diameter of this glass core is 125 micrometers, and is called the cladding. Inside the cladding, there is the actual core that transmits the data. The cladding is there to keep the data in the core. Diameters of the cores, or the three diameters we are used to have, 9 micrometers, typically single mode application, 50 micrometers for multi-mode. 62.5 micrometers was in the beginning, or in lower class fiber optics. Core diameter is going to replace worldwide now with the 50 micrometers. And still mentioning the plastic fiber, it has a coating of cladding of 1,000 micrometers, and the core is pretty thick. It's 980 micrometers. Excuse me. To give you a little comparison, what is 125 micrometers? 125 micrometers is about the diameter of an ordinary hair. So a hair has about 90 to 100 micrometers of diameter. So we are talking here in transmitting the data in a hair. Okay. So colleague also found very nice pictures about a few effects which are important to understand how data transmission works. And he collected a few pictures and a few words which are interesting or important to understand in the world of fiber optics. So it's refraction, reflection, it's an angle of refraction, and the density, the optical density of a media. What you see here is what everybody has seen already. If you put some sticks in a glass of water and you look into this, it's very hard to follow where the sticks really end up. Or when you see it on this picture here, it looks like these two sticks are broken and the sticks look bigger inside. So where is this happening? The sticks are not broken. It's just a different optical density of the media, the air and the glass and the water is different, and each difference gives you a different impression and a different refraction angle of the viewing you do. And this is used to transmit data. How is the data transmission working? It's using different refraction indexes of refraction between the core and the cladding. So if you use different indexes of refraction, you can save light which is going through the core. You can keep it inside of this core by a different index of refraction from the outer cladding around here. So two different types of glass are used to lock the signal here into the core. Each time the signal is going to an edge here, to this border to the other glass type, it's reflected. And you see, that's the way to lock the data into the core of the fiber optic. That's the basic principle. Okay, and there are three kinds of fiber optics nowadays. This is more disappearing. It's a step index, so you have only two different indexes of refraction, and this is giving you this behavior how to transmit data. Nowadays, we are talking about graded index fibers and multimode. So there is not one index for the cladding and one index for the core. There are dozens of indexes here in this core. And this allows us to get these signals a little bit more concentrated over the traveling here to the end of the link. Okay. On single mode is again a kind of a step index again, because I have only one small core here with 9 micrometers with its own index of refraction and the second index of the fiber optic cable outside the cable around it, or the glass around it. Okay, so that's the three typical kinds of construction of a fiber optic cable. That should be for the day on this. Okay, now it comes to the properties of this glass. Property, as I said, is attenuation. That's one of the most important properties we had. And we have different categories, different performance classes of fiber optic cable. And these different performance classes are expressed in attenuation or per kilometer. And here we have the different classes. I don't want to go into too many details. So the categories are OM1, 2, 3, 4, 5 currently. And these categories using different cores inside. So the OM1 and 2 is typically using 62.5 micrometer core. Allowed attenuation by the standards for this cabling is 3.5 dB for 850 nanometers. If we come to 1310 nanometers, we are down to 1.5 dB. Remember this curve, the attenuation curve. So higher the wavelengths, the lower the attenuation should be or is. Okay, you see the different color codings here as well. This color coding is standardized. That's very nicely. So if it comes to higher bandwidth data cable, you see these aqua here, and you see this one here, this purple one, and you see the green one. So this is standardized. You can see usually from the outside of a cable what quality, what performance level does it support. Okay, we have the yellow ones. This is single mode, OS1 or OS1A, and we have OS2, which is currently the best performing single mode with an attenuation of 0.4 of a dB on a kilometer. Fantastic. We also have down here the plastic fiber, and you see the attenuation here is by far higher as we use in the data communication. Another important feature is the maximum or the minimum modal bandwidth it supports. So this gives an indication about the speed we can transmit over these different types of data cable, of fiber optic cables. I don't want to go to the table. You can read it afterwards if you download, for example, this presentation. It's not very interesting for us on the measurement side because actually these good performance parameter, the modal bandwidth, we cannot test in the field anymore. That's something for the laboratory use or production side. So what we test on a fiber optic cable is more installation related. Did something break during installation? Do we get problems on the link during installation? A few side comments from the colleague here. Okay, difference between OM4 and OM5. OM5 was designed for short wavelength dense multiplexing, which requires more carriers on different wavelengths. But that's detail I don't want to dig into too much. Okay, now we defined the properties for the cable. What do we terminate now to the cable? We are terminating a fiber optic connector, and here we have a typically representative of a fiber optic connector. It's called the SC connector. What are the components of a fiber optic connector? It starts first from the outside, from the housing. The housing, what is the job of the housing? The housing is giving the mechanical design of the connector. It's giving the mechanically fitting into the coupler. By the way, most of the fiber optic connector connections are connector to connector, plug to plug, and in between we got optical couplers. So it's not female-male story as we have on RJ45 on copper, for example. Here we always connect connector to connector through a coupler. Okay, very important. So the housing is doing this mechanical connection. And then we have in the inside, we have the ferrule. The ferrule is the part which is guiding the fiber optic cable inside, the glass inside through the connector. Inside, in the center of this ferrule, there is sitting the fiber which is actually doing the data transportation. The fiber consists out of the cladding and the core, as we saw earlier. Okay, is this the only connector type? Oh no. It's very different than copper. In copper, we are used to have only one connector, the RJ45 as mentioned. In the fiber optic world, it's far different. We have a full table of connectors. Before we look to the table, we also have different cut types of the connector. The different cut types you can see here is PC, which means physical contact. So the two connectors are physically touching each other, and the area where they touch is defined by the cutting shape of the connector tip. And there are a few mentioned here. It's PC, which is a pretty flat one. Then we have SPC and UPC, which is a bit rounded one. So to minimize the area of contact and to optimize them, and you see this on a few parameters, like the reflection, how much light is transmitted directly back to the transmitter, which is important to keep that number very low. So not to keep the number of reflections very low, not to have too much energy directly sent back to the transmitter. We want to have the light sent through the cable. For the long distance, we have a typical cut shape. This is APC, angled PCC, and we have here a connector, you see it on the very end, with a angled tip, and this is 8 degrees. This has a couple of advantages for single mode transmission on long distances. Okay, let's look to the different shapes and housings of these connectors, and you see here is a long list of typical connectors used in our environment. I think the most dominant ones are these three ones you see here highlighted now. It's the SC connector, the FC connector, and it's the LC connector. Okay, that's all about this. Okay, so now let's dig again into the transmission of the lights. So how does it work now in the fiber optic cable? So here what you see are the two different types of cable, multi-mode cable, single mode cable. Who is sending in the lights? So on a multi-mode cable with a very thick core of 50 micrometers, we have either LEDs or we can use VCSEL laser, as it's called, semiconductor laser. And you got a certain angle here where you can transmit the light, inject the light into the data cable. This is called the numerical aperture. Okay, and if a light is within this injection angle, the light travels through the core here. And you see we have different lines here, different parts of the signal called modes, multi-mode. These modes are going different ways. And going different ways means that part of the signal are very quick through the core, others take a bit longer. And this leads on multimode to a problem. It's modal dispersion called. So the pulse, which is very sharp when it turned on here and transmitted in, is extended. And of course, the amplitude goes down because the content of the pulse can't increase. And what's happening is if you send now two pulses very quickly, one after the other, these two pulses might end up in one very long pulse with very low level. So there are certain limitations on multimode for long distances and also for too high frequencies transmitted, to high protocols, high speeds. Okay, if you want to go long distances, you cannot allow multi-modes. You just use one single mode, one individual mode, one beam of light to go through the small core. And this allows us, without this modal dispersion, to go a long distance. We have certain attenuation factors to lower the amplitude, but the pulse itself keeps pretty sharp. There is a chromatical dispersion, but this would lead too far today. Okay, but this is the way to go long distances is single mode fiber. Okay, why not to use only single mode fiber? Because the active system combined with the passive cabling is cheaper for the multi-mode as a single mode system. Actually, the data cable, a single mode cable, is cheaper than a multi-mode cable because it's easier constructed. But what you need here is the injection, is the laser part. The active part is still more expensive than the multi-mode part. Okay, so this is why we still have the mixture of a single mode for the long distance and a multi-mode for the backbone in a building, for example. Okay, what is now disturbing this very nice flow of the light signal? There are some disturbers. And part of these disturbers are called intrinsic coupling losses. So they are appearing when trying to connect two different fibers. One which is very prominent is a different core diameter. For example, you are combining two different brands of fiber optic cable. Cheaper one may be, or the shape is not round, 100% round of the core. It's a little bit oval, something like that. So you have some trouble here when putting or when bringing these two fibers together, when splicing these two fibers together. And this is causing, of course, losses, and if it comes to the worst, reflections as well. Then you got maybe two different brands of cable, two different types of cables, two different numeric apertures. If you have still two different numbers, there might be light leaving here, which does not enter the other fiber here. Could happen. Okay, and what else you can accidentally connect is different refractive index profiles. So you got here a step index fiber and you melt it, you splice it together with a graded index fiber. This will also cause definitely losses on this point of connection. This is intrinsic coupling losses. Then we have extrinsic coupling losses, and this is more to do maybe with a connector that is used. And for example, one of the worst things you can do is if you try to pull two connectors or put two connectors together and you leave an air gap in between. What's happening here is you get a different index of refraction through the air here between your glass ends. And this is causing a lot of losses and reflection. You lose a lot of signals. Then you can have radial offset. For example, if you have very unprecise cheap couplers, you have to think about it on single mode. You have to focus 2 9 micrometer cores in a mechanical coupler together. If you use a cheap one and you're just shifting it up by 1 micrometer, you are already getting enormous reflection and losing data of this. So make sure always to use proper couplers to avoid any radial offsets or shifts in this. Another thing is tilt angle error. So this can be a faulty plug where something is wrong and mechanically wrong, or a coupler, or some actual force. Sometimes you see it when you open a rack that the fiber optic cables are very much under stress, and a lot of force is put on the fiber optic couplers or the connectors, and this can lead to this one here, that you don't have a really straight pass through of the light, and this will definitely cause losses and reflections. Okay, and it comes even worse if you look to the end faces of connectors. There can be dirt, for example, between the end faces. We'll talk about this at the very end of the presentation about dirt and contamination. So if you get some material in between the two glass faces, it could be that nothing travels through again. So that's very obvious problem, and one of the most problems we have in data communication over fiber optic. And then we have sometimes people who are combining not matching cutting types of a connector. So here you got a APC connector, an angled connector, and here you got a PC connector, which is straight. So you got here an air gap in between. This can even break the connector, but you definitely lose a lot of energy here and you get enormous amount of reflection. Okay, what else here? Some reflection loss. I think this is pretty much similar to an air gap. You can also have this when having a connectors put together or something went wrong on the splicing procedure. Okay, this is trouble which can affect the performance of the links, and this is trouble we can find out by doing measurements. So let's look to the measurements we can do on a fiber optic link. What you see here is a nice table out of a standard, and you see the performance parameters you need to test copper. That's the one we discussed yesterday very briefly, and we will do it next week very exhaustive. And if you look now to the side of fiber optics, you'll see there are only a few parameters you're testing over there. These are the parameters which are related to installation. So the good properties of fiber optic cable, as you could see, the model, this bandwidth, and all these kind of things, we can't test in the field anymore. Field testing is just an installation testing. So we take away the very nice things here in copper. Yes, come on. So that's what stays is just attenuation, the loss of the energy and the length of the cable. That's more or less what we do. And we also can analyze where events are, where trouble is on the fiber, but we will see when we talk about the instrumentation to do this. Instrumentation we can do to test the measurements. Here again, the sorting on the verify, qualify, certify system again. So a very basic verifying is to use a VFL, a visible light source, where you just put visible laser light into a patch cord, for example, a fiber optic patch cord, and you see whether it turns out on the other side properly. Or you check the polarity of a fiber optic link consisting out of two fibers. That's very basic testing. Okay, then you have the qualifier. Qualifier, I told earlier, the qualifiers are testing using the protocol already. I think there's a slide following talking a little bit about qualifying. And finally, certifying. Certifying, there are two ways to do certification of a fiber optic link. One is to do just the pure attenuation measurement, the length measurement, and the other one is to add to these measurements an OTDR, an optical time domain reflectometer measurement, and this measurement will give us really a clear view on the events of a cable. So let's start with the qualifying. So here's the slide. It's I think out of our website for the NetExpert XG. It's qualifying. It's about qualifying, how qualifying works. Actually, qualifying is really you put a data stream, you set up a data stream between the two ends, and you're looking for lost information, for lost bits. It's a bit error rate testing. What this NetExpert Extra can do is called Lifelight, and it's some patented system. It can give you a indication of the attenuation values over time. So if you got some loose contact on a fiber optic link somewhere, you can manipulate the cable, and you see live and online, you see the behaving of the attenuation value. That's about qualifying. But we are more interested in the measurement of losses and lengths, and what we see here is the principle of loss measurement. When you do a loss measurement, actually, there are 3 steps you have to do nowadays, or 2 basic steps. The basic steps is to reference your measurement system, and the second one is to do the measurement. Referencing, what does it mean? Referencing is checking the test reference cables, and is also zeroing out the influence of the measurement cables. Because when you do a measurement, you always use test cords to access your link under test. You never ever plug in directly a link under test into a test instrument on fiber optic. Okay, there is always a test link in between, or on an OTDR, there's also a launch cable or tail code in between. Okay, so the first step you have to do is to get these influence, the attenuation of the test code out of the game. And what you're doing is you zero it out, you do a field calibration on this. So you're connecting the light source and the power meter on the other side and zero it out. Okay, make sure when you have done the zeroing, never ever detach the test code from the light source, because this is a very critical connection here. Okay, the next step would be, after checking or zeroing out the test reference codes, is checking the second test reference code. So you are opening up the link here on this side again. On this side, on the power meter, open it up, put in a coupler, and put the second test code in. Okay, and then you do a measurement, the first measurement, and this measurement has to be within a certain range of values. It has to be, oh, sorry, it was too far. Has to be below 0.1 or maximum 0.2 of a dB. That's analyzing the second test code. Okay, now you're aware that your test codes are zeroed out and of proper quality. And then you open this connection up in the middle and put in your device under test, your unit under test, the link you want to test. And then you do a measurement, and you see the reading, 3.27 dB is the attenuation you measured. That's so far not a pass-fail statement immediately. Then you combine this against the calculated or a given limit value, and if the limit value is higher, you will get a pass. If the limit value is lower and your value is worse than the limit, you get a fail. This way to zero out the test reference codes, this is the single jumper reference method, the method of choice. There are 2 other methods. We'll talk about that next week. Okay, but this is the method of choice, definitely. Okay, that's the way how a loss measurement is working. If you want to get more information and you want to get some local information, where are my events, where are my connectors, where are my splices on a cable, that measurement is not sufficient. There you need to involve another instrument called an OTDR. An OTDR is an instrument which is doing its measurements from one side only. And the information about the link you're testing is generated on one port. So you send in information, you send out light, and you get some reflection back, and this reflection is analyzed and gives you an overview about the performance and about the location of events on your fiber optic link. Let's go a little bit deeper here. This is how it works. So it's sending out pulses, and it's getting back reflections from every single point of this fiber optic line. It's getting back reflections, which reflections are analyzed and brought into relation to the transmitted pulses. And what again, at the end of the day, is this kind of waveform, this kind of trace, as we call it. And the different parts of the trace are giving us an indication. What do we have here at that location? Do we have a splice? Do we have a connector? Do we have the end of the fiber, for example? What do we have? So you need some analyzing of this reflection. Usually a modern OTDR is doing this automatically. And what we can do with an OTDR is we can get the distances and the lengths, and we can get attenuation values and reflection values. So that's the master class of testing, as I call it over. But more details on this next week again. Okay, now the point I usually mention in presentations always before I talk about measurements, because it's so important. Because it's so important, you have to do it each time before you do a connection on a fiber optic cable. You have to see whether the connector end face is clean or not defective, not broken. The glass is still completely intact. Because if you connect dirty connectors together, you might get real trouble in getting light traveling through this connection. So you have to make sure that every connector is really clean. And there is a sentence, a motto we have. It's called inspect before connect. So each time when you plan to do a connection on fiber optic, you do an inspection before, and if necessary, you clean it properly, your end face connectors. So what we're talking about is the end face here. This part of the ferrule where the fiber comes out, or fiber is in the center. And it's about the size. The ferrules are varying between 1.5 and 2.5 millimeters, and the fiber of interest has a diameter of about 125 micrometers, and you can't see it with your normal eye. What you need definitely to make a statement about the cleanliness of this connector is you need some microscope. When we're talking about microscope, we're not talking about this kind of microscope. They're very spread out. It's a manual microscope where you plug in here, you plug in the fiber, your free connector, and you can visually see, is it good or is it dirty or defective. This does not work if you want to check a connector within a panel on the backside of the panel, because you have to have a free connector to do this. When we are talking about checking the quality of the fiber, we are talking about using microscope, an electronic automated microscope. You see here on the picture, it's attached to the OTDR and gives you this screen. And what is happening in the instrument? The instrument is automatically analyzing the quality of the picture, the quality of the end connector. And there's a standard, and the standard is used to give you a clear statement. Is this connector good enough to be connected or not? If not, either you clean it properly, or if you can't clean it anymore, you have to swap it, you have to change it. Never ever connect two connectors where minimum one of the two connectors is dirty or is defective. It will definitely break maybe the other one as well, or make it dirty as well. Okay, what instruments can be connected? As you can see here, it's of course the OTDR, the high-end instrument, but also the wire expert as these attenuation measurement instrument can be used with a microscope. Also, the qualifier has built in this analysis function, and even our smallest product, high-end verifier, the link master M3, can deliver you this picture. And what is this picture doing? Have a look here at the picture. This is the statement it's doing. It's checking 4 concentric areas around the ferrule in the middle, and it's analyzing and quantifying the dirt or the defects it's seeing. And you have to have all the 4 concentric circles have to be clean under a certain limit of dirt, let's say, that all the 4 areas get the green. And if you get a green, if you have a pass on all the 4, then you can connect and be sure that it's working properly and the light will transmit properly. So where is this part? A quick animation on this. So this is typically a coupler, an optical coupler, and here one side a connector is already connected, an LC connector, to the middle of this sleeve, let's say. Now the second connector is put into this sleeve from the other side, and this point, this is the most interesting point. This is the connection of these 2 connectors. That has to be absolutely clean. Clean means, yep, here are 3 buzzwords we're using. It has to be a perfect call alignment, so make sure that the coupler is not giving you any shift. It has to be direct connected, nothing in between, and you need a physically clean contact. So definitely make sure it's really clean and the connection will work very well. And now the light can travel very nicely within there. If it's not the case, like this one here, this is contaminated. Contamination, like here is a little dust, let's say, in between. This is disturbing the flow of the light. So a part of the light, a high part of the light, will be straight reflected back where it comes from the transmitter, and only a small part will travel on. So you have a very high attenuation here and a very high reflection. And if this piece here in between is maybe a little stone, a little rock in the size of micrometers, it will definitely destroy the glass. So it's like throwing a stone into a glass window. Okay, and if this surface is broken, also you get enormous reflections. So definitely make always sure that everything is clean. You try to connect. Very important. Here are a few samples from a microscope pictures of different contamination you can see. So scratches, fingerprints, finger oils. So some people still think when they clean the fiber optic this way it will be clean. No, you completely do this one here. Okay, so also make sure everybody who is using or working on fiber optics, first of all, you need a microscope to quantify, is it really clean? Is the end face really clean? And if it's not, you have to clean it, but you have to clean it properly. To clean it properly, there is certain material on the market you can buy. What's nowadays very common is these kind of one-click cleaners. How does one-click cleaners work? There's a little rope in there, and if you do a click on this, it's moving a little rope along the top end of the fiber connector, and it's shifting away the dirt. That's very typical, very, very common nowadays, and very easy to handle, and you can't do too many things wrong. If it's more solid dirt and you need to have some wet cleaning, here is the material. In the older days, or the first days, there was used always alcohol, isopropanol alcohol, very high-graded alcohol. Alcohol, in the meantime, is not very much liked anymore. So if you go to wet cleaning, go to a water-based cleaning fluid, special fluid. It doesn't leave any residues on the end face of the connector. What else do we get here? Cleaning sticks and also cleaning paper. There are a lot of professional cleaning tools out in the market, and just check the market what is offering. That's it already for today, for this brief introduction into the fiber optic world. As I mentioned earlier, we have a little series of 6 different presentations. So yesterday was copper basic, today we have fiber optic basic. Tomorrow, an interesting one, we are talking about 10 gigabit Ethernet in combination with testing, a net expert with qualifying, so a little bit away from the structured cabling to the application a little bit more. Next week, we are going to the advanced courses for copper cabling, for certifying copper cabling and certifying of fiber optic cabling. And also the last seminar will be on Thursday next week is about active Ethernet, some basics of the active testing, as I mentioned already earlier yesterday. Okay, I think that's it from my side. I'm now looking to my co-pilot, who has written very much in his little document now in his notebook. And from my side so far, thank you very much for your attenuation. And yes, Frank, showtime for you. Questions?
Yes, hello. There were a lot of questions, and some I answered already. Some are still open. If there is a question open which we don't answer, we take a look after this webinar and send you an email or call you or something like this. Some open questions are, Jose in Spain said that.
Hola, señor.
said that to the hotel, so in Spain there are a lot of PON networks.
Passive optical networks.
With fiber to the home or fiber to the hotel.
Yes.
And there are special testers to test that outside. But his question is how to measure it inside. Is there a standard or?
Yeah, you have to see the network structure as it is in this premises, and if it's the inside link, we are just down to the typical attenuation measurements as we do. So it's more a topic to measure the passive network from the outside as from the inside. So because usually the definition of the PON stops at the building.
Yes, and I already answered. that privately at my home, the provider did the decision to say, for my network, you have to do an OTDR measurement at the last meters, but
yeah, that's always the discussion. What measurement is required? Is it just a attenuation measurement, which is very precise, more precise than an OTDR measurement, or should it be an OTDR measurement, which gives you also a list of events? How is it constructed, your fiber optic link? That's always a discussion we have since years now.
Then there was the question, the link expert M3.
Yes.
What does he do on fiber? Is he doing a qualification on fiber? Or?
No. What the link expert is doing is, first of all, it can definitely qualify the end phase, as you have seen with the picture on the microscope, and it also can get in contact with a network that is fiber optic based. So it's an active test. As you will see next week, Thursday, the active test an instrument can do. It's like getting in contact with the switch and asking for an address, DHCP testing, ping testing. So a certain number of active testing. It does not do any passive testing. What you can do is you can derive some attenuation values roughly, because it's also reading the information which is in the SFP. The M3 is using a standard SFP on top, which is plugged in, and certain SFPs can provide you the level of transmit and the level of receive. So if you do a link, let's say if you do a loop, you can see roughly the attenuation of a fiber optic link. It's not a measurement, it's a determination, as I call it, but it gives you some indication if you're in doubt what's going on.
And I think one more question which I didn't answer until now. What is the best way to clean the end phase?
It depends on the dirt or on the situation you have. So the best way, yes, see what the problem is. The easiest way is to use the one-click cleaners, definitely. If it doesn't go away, you use some liquid to do it and some proper tissues, not the tissue you use for. So use proper material for cleaning. It depends on what you see. And there is an old statement: if you can't clean it with 2 clicks on a one-click cleaner, look at it very closely. It might be even broken. And then you have to throw it away. But there is no best way. It depends on the dirt you have on there.
So there are special fiber cleaners for this, and it's,
yes. There's a broad market, a broad range of cleaning materials. Just stroll through the internet and see what's on the offer.
Yes, I have to see if there are some more open questions. Like I said, we are looking at this and maybe giving you an answer per email or per phone. Okay. I think that's it for today.
Okay, wonderful. Okay, thank you very much for attending this little seminar today, and hope to see you tomorrow again, next week, of course. And from us, I think, goodbye. We will slowly move out of the picture now.
Goodbye.